does seem tricky placing a nuclear reactor in a chemicals factory with, some of the concerns around nuclear, whether it's overregulation or smart regulation.
That's absolutely going to be a siting issue. Look through the Chemical Safety Board history on chemical plant and refinery incidents and sort of the scale of damages, blast damages, missiles, projectiles. I can't see a regulator permitting the reactor to be within the high pressure blast radius or missile radius of that without the kinds of underground or hardening that start really hurting the economic case. Where if you can site your reactor, a couple clicks away from your user and deliver via steam, you sidestep that issue basically entirely.
A warm welcome back to Decouple. Today I'm joined by my friend Jesse Huebsch, whose name I continue to butcher. Jesse is a principal process engineer with a specialty in designing chemical plants. He's also a Decouple veteran. This is his second appearance. We had a great episode on modularity, lessons from chemical process engineering. Jesse, we're going to be talking about process heat today. Very excited to have you back. Thank you for making the time.
Nice to be here and happy to join you.
And killer beard, man. That's a big change from last time.
Thank you. It's vacation beard rolls into fall beard.
Yeah, the weather is starting to turn up here in Canada. So good face insulation. So in terms of this topic, I've been very interested in nuclear's role, how expansive or limited it might be in process heat. That's certainly one of the applications, particularly for more what are so-called advanced reactors, high temperature gas reactors, even molten salt reactors, liquid metal reactors, is that they can provide higher outlet temperatures. And so I've been wanting to give this a fair shot and again, understand what some of the limitations are, what some of the opportunities are, what some of the prospects are. Emissions from process heat are large. About 25% of the world's emissions come from industry, and I think 2/3 of that comes from process heat itself. So there's definitely a rationale there. As well, for certain countries with limited access to certain fossil fuels, there's probably some energy independence reasons as well. So excited to dive into this today with you, Jesse. Again, thanks for coming on the show.
Happy to be here.
All right, so I guess we should start just by talking more generally about process heat and what it is. So why don't you give us a little kind of a short overview of that?
Yeah, so we keep hearing about process heat as sort of a general background, and typically you hear headline temperatures about what temperature heat's required, but what the discussion usually leaves out is what is that heat actually doing within the process. So generally, process heat is used to drive either chemical reactions, particularly what are called endothermic or energy-absorbing chemical reactions, as well as phase changes. So a canonical example would be like baking a pancake or cooking a pancake, where you have a batter that has a bunch of water to make it into a slurry. You put it into a hot pan. While you're cooking it, you raise the temperature of the batter and you drive off a bunch of the water by turning it into steam. So you get a drier end product than what you put in, as well as you drive a bunch of chemical reactions that denature proteins, bond them, form cross-links between the various starches and proteins, and you end up with a cake instead of a cracker or a bunch of dry powder, what you'd get if you just heated up some flour. Fundamentally, at most temperatures and for most industrial uses, those are the two or three main aspects involved: raising the temperature of stuff to get it to the point where you can do stuff, and then driving chemical reactions or driving phase changes. Phase changes can be used for separating out different reactants and products in the end, or fundamentally that's to do with your product. So say for making metals, if you need to turn a solid metal into a liquid metal to be able to cast it or turn it into plates, that's another phase change where you're melting the metal. Or, for example, in cement making, where you're driving a chemical reaction, which is splitting the carbon dioxide off of limestone to make calcium oxide. That's the chemical reaction. That reaction takes a bunch of energy to drive because it wants to go the other way. You input that energy as heat to drive the reaction, and then you're relying on the phase differences to separate the different parts of that and keeping only the part that you want for next stages in the process.
And so Václav Smil talks about these 4 pillars of civilization. I was giving a talk on net zero in Australia recently and just noting what a daunting challenge it is to decarbonize these sectors. Part of the story there is process heat, and part of it is the reducing agent. So if we're looking at steel, for instance, I was running some calculations and looking at some research. And just to create the hydrogen for all of the steel making in the world, the primary steel production, not melting the secondary steel, we need 4,000 terawatt hours of electricity. That's essentially the entire electricity production of the United States. That's just to make the hydrogen. But then we also need to obviously melt the iron ore as well. So I think it might be fun to just, you mentioned cement. That's it's one of Václav Smil's pillars. We look all around us. Modern civilization is very dependent on that. Maybe we should just go through steel, plastics, and ammonia. I think, again, just to drive home the relevance of these processes and discuss sort of what's necessary in terms of the process heat required to drive these processes.
Yeah, sure. Let's take them one at a time. They're each, of course, very unique. But the other interesting aspect here is to contrast what's the traditional way of doing them and what would be some of the potential future routes, and how does that impact both the process heat and what formats the energy going into it are required at. So starting with steel. So traditionally, steel is made by a blast furnace where you use coal or coke. You partially burn the coal to make carbon monoxide gas. That makes a bunch of heat that you need to get to the appropriate temperatures to drive the reactions as well as to melt the end product. But fundamentally, you're after the carbon monoxide. That's the reducing agent you mentioned. And its role is to grab one of the extra oxygens off the iron oxides that are the iron ore. So the carbon monoxide grabs a oxygen off to turn the iron into elemental or metallic iron instead of iron oxide. And by doing that, it turns into carbon dioxide and then is evacuated from the process. That leaves you something that's then hot enough to be a liquid stream that comes off and goes downstream for further processing. In the traditional process, that's a blow with oxygen to remove the residual carbon that's left after the coking process. But effectively, the blast furnace is the big user of energy and heat, and everything downstream is cleanup and post-processing and purifying and stuff like that. So where we potentially are going, a number of different routes, but the biggest scale one is what's called direct reduction of iron. So in that case, instead of using coke to make that carbon monoxide reducing stream, you're using either natural gas or direct to make a syngas, which is a mixture of carbon monoxide and hydrogen, or using hydrogen supplied from elsewhere directly. Both of those are acceptable reducing agents for the process. And it operates at a bit lower temperature without really needing a independent heat input. The heat from the reaction essentially drives it. And it does not end up producing a liquid product, so it operates at a bit lower temperature. But again, it's a chemical reaction that's driving pretty much everything involved in it, rather than needing large amounts of separate from the chemical reaction heat input to melt the metal. Downstream of that, you still need to make the metal into a liquid to cast it or turn it into plates or whatnot. That's typically done in an arc furnace, which is you run an electric current through the iron. The iron is actually your resistance element. Run enough electricity into it, it makes it hot enough that it starts to melt. Traditionally, that has been used for recycled steel, but there's no fundamental reason why it can't be used for higher grade virgin steel. It's more about the contaminants that come from the recycled steel that gives it a reputation of having lower quality outputs rather than anything fundamental to the downstream aspect. So in the past, we used a lot of coal or coke, metallurgical coal, to make combination of heat and chemical use, and then a further bit more fuels to drive the melting and downstream processes. The primary likely future case, we use higher value or higher intensity chemical reducing agents, where more of the energy involved in them goes into the reducing, and then electricity downstream to finish the conversions and the processing.
And in the present tense, I think it's 99.9996% of the world's primary steel is done the old-fashioned way. So there's a potential future here, but
a significant amount is actually done by the DRI approach, just mostly via natural gas, rather than directly hydrogen or especially clean hydrogen. So there is a substantial install base of the DRI. It is not a low tech readiness level product. The pure hydrogen is somewhat lower, but it's not drastically different than the process that we already have. So from that standpoint, it's the most straightforward of the various processes to convert, because we have this base of other ones, especially if we lean on doing DRI processes that are partially substitutable by pure hydrogen addition or flexible in how much of pure hydrogen they use. Then we have the opportunity to use hydrogen when it's available and switch back to natural gas when it's not. Over time, the intent would be that there's more hydrogen more of the time and from clean sources, and that more and more of your output would be from clean hydrogen to steel instead of riding on the fossil fuel supply.
Got you. So that 99.996 figure is related to green hydrogen,
yes.
Reduced steel, I guess. Okay, gotcha. That's an important distinction. Okay, so we talked a little bit about cement, but I thought plastics was interesting because this is one where it seems to be, particularly for ethylene cracking, and that seems to be the basis for a large amount of the plastics we have around us, from our Tupperwares to styrofoam, et cetera. That's one that's just very much heat driven, not a chemical reaction that's occurring.
In terms of the external energy supply, yes, it's heat driven. It is driving a chemical reaction in the process, but we're not, the chemicals that we put in as the feedstock have all of the chemicals needed for the various reactions. So a mixture of steam and hydrocarbons goes in. We supply heat for the endothermic, again, energy absorbing reactions that are happening in the process. Currently, we tend to do that using what we call indirect heat. So that's heat supplied via a heat exchanger, as opposed to when we were talking steel, we were doing direct heat, where we mix the fuel and the heat carrier directly with the process. So indirect heat is like a pan on your stove, where your direct heat is like shoving your marshmallow in the campfire. So the big challenge for indirect heat is that as you get higher temperatures, you start to need more and more exotic metals. And once you get above 800 degrees or so, you're well into the unifordium at scale kind of range, if it's even possible or chemically compatible with the process at all. So the cracking is probably one of the highest temperature applications that is actually normally done via an indirect route, typically in the 600 degree C range. Currently, that tends to be done via running, basically burning some form of fuel in the outside of a shell and tube heat exchanger. So often burning that directly in the heat exchanger, and then having the gases that are reacting be on the inside of the tubes in the heat exchanger. That's the one that, because it's an indirect approach, has the at least tantalizing potential to be supplied via nuclear heat of a quote unquote advanced type, one that can deliver the kinds of temperatures that are needed. The big challenge there, of course, is going to be, how do you provide the separation between the heat carrier fluid that is directly exposed to the core, and in the event of a fuel pin leak, could be radioactively contaminated, and putting that in non-nuclear rated process vessels, and how much separation and how many steps down of temperature is required to achieve that, how many exotic and expensive heat exchangers. Now, going into the future though, there is a significant amount of development work on doing electrically heated crackers. The reason that has the potential to be successful was because, as we're describing it, it was indirect heat. Electrical in a resistance element is just another way of providing indirect heat. So essentially wrap resistance elements around those tubes, and if you can find the right type of elements that tolerate that heat and the right control and bonding and stability and stuff like that, you can deliver that heat where it's needed into the process. The other aspect of that that's interesting long-term is where that industry may go in a reduced or post-fossil fuel world. And that will be shifting probably primarily to turning methanol into olefins as opposed to turning hydrocarbons into olefins. So that process runs more in the 300 to 400 degree range and is much more in the range of conventional types of steam to be able to supply that kind of heat. That's likely where pretty much any either gasification or biomass is likely to be turned into something like methanol, used as a base feedstock, and then turned into a myriad of other products from there, if we are to ever get away from the fossil fuels being the primary carbon supply to our economy.
Okay, and so this would be stringing together methanol to make plastics into longer
Yes.
hydrocarbon chains?
Yeah,
Okay.
so it's the you make syngas to make methanol. You use the methanol there's a number of different chemical pathways to make different products, but you can turn methanol into ethylene and propylene, and then ethylene and propylene being the primary alkane or olefin monomers to make most of the plastics. Some of those can be transformed into some of the larger, like BTX, benzylene, xylylene, toluene types of chemical building blocks to make most of the rest of our types of plastics, polymers, and other chemicals.
Whereas right now, longer hydrocarbon chains are cracked using heat to make all of these various ethylenes, which
Typically,
form
yes.
the basis for. Okay, got you. Okay, well, let's race through ammonia and then maybe get back to some basics.
Yeah, so ammonia is probably actually the most easy to substitute because ammonia is combining nitrogen and hydrogen. Fundamentally, nitrogen you get from either air or from an air separation unit that's electrically driven already. So substituting for different sources of electricity to get that is straightforward enough. And then ultimately, ammonia is the story about how much energy do you need in what forms to make the hydrogen. Hydrogen utterly dominates the energy requirements for ammonia. So it really, take a step back, and it's the hydrogen question. So how do we get hydrogen going forward? And you basically have what's currently gray, or could be in the future blue hydrogen, which is fossil fuels, either unabated or with carbon capture to make a hydrogen stream, or you have electro-based hydrogen, so water electrolysis from any electricity source, or steam electrolysis where you use low-pressure steam as a feedstock instead of liquid water, and then with a smaller amount of electricity. Again, the electricity can be from any source, but ideally in our future would be from various clean sources to make the hydrogen that you need to then run the ammonia plant. The ammonia process itself needs some heat, but it also throws off a fair bit of heat, and it's at the kinds of temperatures that can be derived from steam as a transfer medium. So from that standpoint, it's somewhat the cleanest substitute in that a lot of the base technology for the actual making of it doesn't necessarily have to change much. Some of the existing facilities are optimized, assuming that there's CO2 present in it, and obviously that would need to change. But the basic flow sheet and technology for it isn't drastically different, using only hydrogen and nitrogen as inputs instead of a syngas stream and nitrogen as the input.
So just using these 4 examples we have now, we hear that it's a lot more complex than just supplying a certain temperature. We have in some cases heat exchangers that are involved. We have direct, indirect heating, and we have processes where, in the case of cement, you just need to provide a lot of heat, and the chemical reaction itself is the majority of the emissions. Whereas processes like ammonia, if you can get the hydrogen from a low emission source, that's the majority of the emissions there.
Yes.
And I guess steel's kind of somewhere in the middle. Let's talk a little bit about the various grades of heat. I'm not even sure if this is an accurate term, but like low grade versus high grade steam I've heard of, for instance. But, we have to produce heat at different temperature ranges for different processes. From what I understand, nuclear is, the high temperature reactors are capable of producing, maybe theoretically having outlet temperatures, in some of these very high temperature gas reactors around like 900 degrees C. But of course, as you were saying, the working fluid in the case of the high temperature gas reactors, the helium, we can't use that in a direct fashion. It has to go through a heat exchanger and it loses a bunch of its temperature. So walk us through some of those considerations and again, the uses for different temperatures.
I mean, let's take a gas turbine in a combined cycle as an example, because walking all the way down from the very top to the bottom kind of gives us an overview of the different kinds of heat that we're talking about. So in a gas turbine, you combine a fuel and air or oxygen in the combustion section of the turbine, where you can have heats that range from 1,500 degrees to 2,500 degrees C. That heat is then used in the turbine in a mechanical means where by losing pressure, it also loses temperature. That change creates momentum. The momentum spins the turbine and you capture work from the shaft. You can turn that to electricity. You can drive a compressor. You can drive other pumps or other operating equipment. In a combined cycle or a cogeneration plant, the exhaust from that is typically in the 500, 600 degrees C range, where you still have enough temperature to, in a power plant, boil water, superheat it, and to generate what would be called high pressure superheated steam. So that might be 60 times atmospheric pressure and 500 degrees C. There's a number of variations on pressure and temperature combinations, but that kind of high pressure and temperature is really good for making power, because you can get a very high thermal efficiency out of it. You have a lot of residual energy between the energy that has and the very low pressure steam that would be coming out of the very end that you're just condensing to move it out of the way to pull more steam through. So as you work your way down sort of that utility chain, first you'd give up the superheat. So some chemical processes need that very high bleeding edge of the temperature, and you're just reducing what's called sensible heat. So it's the temperature you measure or the temperature you'd feel, not that you'd want to feel high temperature steam, as you get down to where it's saturated. When it's saturated, it's called latent heat, and that's where it's starting to condense. So steam has a lot more energy from the condensation than from the cooling down the superheat. So where you really need it to drive a process, you use the superheat to get that temperature. As you go down a bit further, so get down to call it 300 degrees C, you're getting into the range where it's practical to have saturated steam. That saturated steam gives up its heat by condensing. The nice part about it when it's saturated is the temperature doesn't change until you condense it all. So you can deliver, if you have 300 degree saturated steam, you can deliver an enormous amount of energy and be at 300 degrees the whole time while you're delivering it before you end out with a lower temperature liquid condensate. It's still warm enough to recover some useful heat, but it's much more limited applications. And that's really where the quality parts of it comes in, is the higher temperature and pressure it is, the more options you have for what you can do with it, and the more work or electrical power you can extract from that source by letting it down. So another common approach would be in that cogeneration approach. You started with that, call it 500 degrees C steam. You can run it through a turbine. If you want to run it all the way down in a conventional power plant, you'd be running it down to about 1/10 of an atmosphere. So 0.9 atmospheres of vacuum below atmospheric pressure, and then using cooling water to condense the remaining bit of it into a liquid stream. That condensing pulls the gas into the condenser, and it's really that momentum change that is driving the work rather than strictly the temperature or pressure change. Or you can pause that cycle partway through and extract some of that steam at, let's call it 4 or 5 atmospheres or 150 degrees C. And there's a number of other processes that can use that lower temperature, but you're getting more into conventional heating processes. So where you need to run a dryer or an evaporator or a lot of food processes, they're dealing in that sort of type of temperature range. So you've taken your high grade steam, dropped it to low grade steam, made some power in between, and now you have another crack at using that lower grade steam, but it has a more limited set of options for what you can use it for. And so on, you go down and you become more and more limited to what you can do with it, till ultimately, essentially, your options are like building heat, where you're trying to, heat up a building to 20 degrees C when it's cold outside. That's kind of the very bottom of the ladder of what you can get useful heat to do. But again, you're getting into more limited and circumstantial uses.
So what you described there sounded like a combined cycle gas turbine largely, and then you talked about other uses as you degrade the heat. And as a process engineer, you're trying to extract as much value as you can from having heated whatever working fluid up that you did in the first place. And there's a lot of elegance to that. Let's walk our way through, say, a high temperature gas reactor there in terms of producing the heat, and what comes next, and ways in which you could use, again, it sounds like we can't use the outlet temperature and the actual coolant itself for risk of radioactive contamination, but how that would be used in an ideal set of processes to extract as much value, and what kind of applications you could run.
Let's start with our 900 degree C core exit temperature gas reactor. So it's a gas coming out. The challenge with gases is they're actually terrible heat transfer fluids. So you tend to need bulky heat exchangers with a lot of surface area. And at that temperature, it's an expensive metal. So you need a expensive heat exchanger to transfer that heat to another loop. Assuming that you're trying to keep it up at that temperature, you're going to another gas, because there aren't really much in the way of liquids that have the combination of properties that make them, safe as a heat transfer fluid, as well as, the attractive properties for that. As a intermediate loop before you'd go to your ultimate destination. So this would be possible to do with like a helium loop in the primary, and then some sort of inert loop, helium, carbon dioxide, something like that in the secondary loop. And then in the case of our steam cracker, you could put that into the shell of the steam cracker, and then return it back to the secondary loop. Each of those loops then needs to have some sort of fan or compressor to motivate that fluid to keep circulating, which of course has its own leakage and energy costs associated with running it, to come back and complete the cycle. So that's really the most likely application for really high temperature nuclear as process heat, because it's already a process that uses indirect heat. It's in vaguely the right temperature range. The material compatibilities are tractable. Whether it's economic, this is another question.
Just so I understand those loops, you have the reactor coolant, and then interacting with another inert gas in another loop, and then you're taking that gas and running it into your ethylene cracker. What is it interacting with? Is heat just coming off of metal pipes and interacting with hydrocarbons directly? There's no steam involved?
So in that case, no, there wouldn't be any steam involved. You'd be putting it essentially in the shell of probably a slightly redesigned, but not fundamentally different steam cracker, and having that heat be absorbed into the hydrocarbons through the metal walls of the tubes. The hydrocarbons, when they react, are consuming heat or absorbing heat, so they're running at a lower temperature than the gas is. So they'd be pulling heat out of that gas. So at the exit of the shell, the gas coming out is going to be at a lower temperature than we supplied it to in the first place. The headline temperature of the process, typically the actual process working temperature, and then you need to make it a practical amount of heat exchange area, 20, 50, 100 degrees, depending on the fluids, of higher temperature fluid, heat transfer fluid exiting the exchanger, and then a step higher yet to have enough usable heat to transfer by dropping the temperature of that fluid. So to deliver, 600 degrees, nameplate working temperature for that steam cracker, you're probably needing to deliver 800 degrees C carbon dioxide to the heat exchanger in that secondary loop.
Okay.
So from our example, we don't have a ton of margin, but it is possible to do that.
Right. And so again, just to clarify, when you say steam cracker, this is just the vessel. There's not actually steam in it. But
There is steam in the hydrocarbons. So the steam is actually a reactant for the process itself, as opposed to a steam heated vessel where you're using steam as the heat transfer fluid. So yes, that can be somewhat confusing in the naming.
And so that steam is going to be supplied by another form of process heat and then fed in with the hydrocarbons and then get more heat off of the gas inside that secondary loop heat exchanger.
Yeah, you could essentially take your hot product and in cooling it down to something that you can handle later, you're giving off some heat that you could use to boil some water to make that steam, for example, or many, many, many other options in such an integrated process. But, everywhere you look, there's changes in temperatures for various processing aspects. And that's essentially the job of process engineers, is to find each of those usable bits of energy and put it to use. Because, the vast majority of the cost in most processes is feedstocks and energy.
You were mentioning once you get up to these higher temperatures, you start running into alloys which are unaffordium. I'm not sure if they're unobtainium, but there's a lot of stress that's put on these metals. And again, if you're needing to keep that radioactive primary loop separate from the secondary loop, there's the potential for cracking at that heat exchanger, and that seems tricky.
Absolutely. I mean, that's where an enormous part of the expense of direct supplied at high temperature nuclear heat would be that you need more of those heat exchangers. Those heat exchangers have to be spectacularly robust. Some of them get into doing even double-walled heat exchangers where you have a tube within a tube and a void or a sentinel fluid in between. But that obviously, at least doubles the cost. It makes the heat transfer worse, so you need a larger step in temperature to make the, same heat exchanger area workable. So there are ways to address it, but it adds cost. And that's ultimately the challenge here is how do we deliver clean heat as cost effectively as possible and as consistently as possible. That's the other aspect of a lot of these, especially higher temperature processes, is they don't tend to like variation. They want to run steady. Starting up some of these processes can be a matter of days to weeks, not minutes to hours typically. And of course, every time you change the temperature, you're imposing stresses on all your metals, your heat exchangers, your refractory, and thermal cycles can be essentially what governs the life of a lot of the equipment.
And presumably a lot of the operations and maintenance and outages might have to do with cracking the heat exchanger, contaminating a secondary loop, needing to shut everything down, get rid of that secondary loop gas, treat it, whatever. So potentially pretty buggy compared to existing processes, which are pretty well understood or don't require a whole other secondary loop. You're saying you can just combust gases right within a heat exchanger itself. I think that's what you're describing. Contemporarily is done for ethylene cracking.
In that one particular one, it's either done directly in or immediately adjacent to, but it's the combustion gases going directly to the shell of the heat exchanger, as opposed to needing a secondary in between. So in the conventional process, you only have one heat exchanger, and that's the process heat exchanger. You don't have other upstream heat exchangers to give you the hot heat transfer fluid in the first place.
In terms of siting the reactor in a chemical plant to be able to deliver this kind of, I know we can move steam a fair direction. I'm not sure how far we can move this kind of direct gas to gas heat, but it does seem tricky, placing a nuclear reactor in a chemicals factory to then do this with, some of the concerns around nuclear, whether it's overregulation or smart regulation to manage source term that could potentially come out of a reactor in the worst case scenario.
Yeah, that's going to be another big aspect. So steam moves, especially saturated steam, moves very nicely. There's a example that's up and running in Lianyungan in China, where they're currently exporting something in the range of 500 megawatts worth of medium pressure, 20 bar steam to a petrochemical complex through a pipeline. I don't remember the exact size, but it's a fraction of a meter in diameter. So very conventional piping, tens of kilometers long, utterly no siting co-location issues there. Where for these kinds of high temperatures, they're gases, so pressure drops are high because velocities are high. Because of the very high temperatures, you need to take up a lot of thermal expansion. You need a lot of expansion loops and other issues like that. It's low density, so the diameters are large. You'd be wanting to be within hundreds of meters, preferably at the very low end of that to use direct high temperature gases as a working fluid. And that's absolutely going to be a siting issue. Essentially, look through the Chemical Safety Board history on chemical plant and refinery incidents and sort of the scale of damages, blast damages, missiles, projectiles. As a canonical example would be the Flixborough incident in Great Britain in the 70s, where a high temperature cyclohexane reactor ruptured, created a vapor cloud, and essentially flattened the whole facility. So you're in a kilometer diameter fireball. I can't see a regulator permitting the reactor to be within the high pressure blast radius or missile radius of that without the kinds of underground or hardening that start really hurting the economic case. Where if you can site your reactor, a couple clicks away from your user and deliver via steam, you sidestep that issue basically entirely.
That's interesting because, I think we tend to think there's this famous example with relation to the Fukushima incident where one of the images that was circulated in media was actually an explosion at a petrochemical facility with a big fireball, right? Which looked more dramatic than the hydrogen explosion at Fukushima. And the two were confused. But you think that the nuclear accident would affect the chemical facility, but potentially the accident at a chemical facility, the explosion could affect the reactor a lot more and then maybe provoke a nuclear accident as well and have a double whammy. But the scale of what can go wrong at a chemicals plant is potentially pretty serious. And you do a lot of work to prevent those kind of things, I imagine.
If we look at the chemical industry history, we have a far higher body count than the nuclear industry. We've tried to learn from that, but there's just a lot of contact points and a lot of it. So it does continue to, represent significant hazards. And if you scan through the Chemical Safety Board or the news about the chemical industry, we can see that those have not gone to zero. So, that's a very good point of the, where is the physical siting of the reactor versus the rest of the chemical process.
Right. And I guess just we're going to move over to turning that nuclear heat into steam in just a second, and you've sort of touched on it. But with regards to this gas process at higher temperatures, needing more complex alloys, more stresses, thermal stresses, potentially more maintenance on those heat exchangers. If you have a reactor system that we're working towards getting good capacity factors out of, but realistically, it took our pressurized water reactor fleet 30 years to start hitting those 90% capacity factors. There's going to be some bugs to work out in high temperature gas reactors, for instance. And if there's unplanned outages on those reactors, that's going to be extra stress on those heat exchangers. And then also you got to think that's going to hurt the economics a little bit. If, as you're saying, you have processes that want to be running, day after day, month after month in steady state, that would be, I guess, another challenge.
Absolutely. I mean, you'd need either multiple units or a redundant way of providing that heat in the downtime, or reworking your process to be able to accept more variable heat input. I mean, that's kind of the case for, the Dow X-Energy project. To my understanding, they're not planning on using the high temperature gas directly for any of the processes. They're planning on using it essentially as the tail of the gas turbine kind of conditions that we talked about in the cogen, and making high pressure superheated steam. And then that steam will be used for various site users. They'll also in parallel make power either from that steam or from the gas. I'm not quite sure which. And then use extraction from that to provide lower pressure steam for the users that need that on site. So it's providing essentially electricity and various grades of steam to the site. And it has, I think, 4 units so that you can maintain most of your capacity when any one unit is out, whether it's for unplanned outages or for planned refueling outages.
So yeah, let's talk now about taking that same style of reactor and producing steam and some of the considerations there. I guess first off, there's a big drop between what your outlet temperature is of your primary coolant and the steam you produce. There's a kind of efficiency penalty to pay there that's much less than the gas to gas that you were speaking of before.
Yeah, and one particular nice thing about making steam is the actual act of boiling is an extremely high intensity heat transfer process. So the amount of surface area you need to boil a liquid is orders of magnitude less than you need for a gas-to-gas heat transfer process. So especially if we're getting into some of the higher temperature but liquid coolant cores, like a molten sodium or lead or a molten salt coolant, then driving a steam generator, the size of the heat exchangers that we need is orders of magnitude smaller than a gas-to-gas heat exchanger to deliver that high-temperature gas. The other aspect is the actual boiling part. You're typically going to be operating in the kind of range where conventional stainless steels are perfectly adequate. You just need to have the corrosion resistance for your working fluid for the reactor core, but most of those typically are also still in the stainless steels. So you're getting into the much more conventional materials, order of magnitude at least less than some of the anaphordium that we were talking about for the high temperature processes. We also have much more experience in turning hot fluids into steam. I'd love to actually try to figure out how many gigajoules of steam we've produced over the course of history, but it's a mind-boggling number. So in terms of the maturity of the technology and the understanding, there's a enormous gulf there as well.
And that seems to be why to date applications for high temperature gas reactors so far have been to be making relatively high temperature steam, not the gas to gas.
The other nice part about steam is because it's so well known and there's so many ways of doing it, you can supply your steam that you produce into an existing site header and immediately reduce the amount of fuel that you would have otherwise used to make that steam without changing your downstream process, without changing most of your site infrastructure. You still potentially can keep your fueled equipment as your backups or your peaking equipment. Or if you wanted to be able to, say, export electricity higher than a normal amount, using more of your high temperature process from the nuclear to do that, while then running a fired boiler to make the steam to keep everything going. It's a lot cheaper and easier way of, indirectly adding peaking capacity than keeping clean, firm power on standby for intermittent use, or keeping, fueled but rarely used electrical production equipment on standby as opposed to just steam boilers. A burner, or let's start at the top. Nuclear plants right now tend to be in the, tens of dollars per watt, working our way hopefully into the lower single digits. Coal and natural gas are in the mid to low single digits dollars per watt. Solar and wind facilities also in that sort of, maybe some solar just edging under $1 a watt. Where stuff like heat pumps tends to be in the sort of $0.50 a watt range for transferring heat. Burners themselves tend to be well under, a dime per watt, and can be approaching a penny per watt in terms of the actual cost of the equipment. So the actual, cost to stay on standby is greatly reduced for just standby ways of making steam or other forms of direct heat, rather than standby ways of making electricity.
Okay, so if we're, say, looking at X-Energy, for instance, and we're getting steam at 565 degrees C, what can we do with that steam? What sort of processes does that unlock?
So that unlocks a number, most, if not all, petrochemical existing users of steam. And that's about the highest temperature user of steam currently. So basically unlocks anything that you can do with steam. So it would be useful for oil sands, SAGD kind of injection, be useful for pretty much any process at a refinery that takes steam. As you let that down to lower and lower temperatures, pretty much the full slate of later stage chemical products, or what would be called the final goods or intermediate products, as opposed to the primary olefins and stuff like that. So the plastics processing, making ammonia, making methanol, and pretty much anything downstream of there. Food production facilities, operating some of the carbon capture, either direct air or like ammonia cycle or amine cycle carbon captures, basically the entire slate of industrial steam use.
So we don't currently produce steam that's much hotter than that. There's not really any uses for steam that's much hotter than that.
We do slightly, but pretty much only in supercritical power plant applications. As far as I know, I don't know of any process uses of supercritical steam, largely because the temperatures and pressures involved are starting to get into extremely thick and expensive components. So you're trying to keep that as compact as possible, and basically trying to take it directly to a turbine, and really you're just maximizing your thermal efficiency at that point.
So again, in terms of trying to understand sort of low versus medium versus high temperature process heat, the high stuff sounds like it's more electric arc or direct heating by burning something in your materials, or firing a flame at something. Am I more or less dumbing that down?
Largely, there's a few slight twists on that. There's some work on using microwaves to try to inject that directly. That has a lot of challenges with just the scale of the power density required to get the, tens or hundreds of megawatts that are required in something like a cement kiln into it. There's also something called plasma heating, where you use a carrier gas and then you heat it up to like 20,000 degrees with an electric current and inject it. But again, there's, scale issues of just getting that many megawatts, the power draw required. So then you're using, more expensive electricity rather than the other energy directly, or doing things like burning hydrogen, Or actually, one of my favorites is you can use electricity to run an air separation unit. You take the oxygen from that. We were talking about those earlier to get nitrogen from ammonia. Take the oxygen, and then you intensify your burning stuff. So basically, in a conventional flame, you have 4 parts of nitrogen for every part of oxygen that's along for the ride. You have to heat that up from ambient. It absorbs a bunch of heat from the flame, and then you have to discharge it from the process at the operating temperature of the process, where it's not useful anymore. So it's dragging off a bunch of that heat with it. Depending on the application, you can get many multiples more, effective reduction in the amount of thermal value of the fuel that you need than the electricity value that you put in to make the oxygen. I've seen some examples that could be in the 20-fold range. I think that's my most underappreciated trick for turning electricity into usable high-grade or ultra-high temperature process heat.
And so this is basically oxy-combustion, which also potentially really unlocks a lot of carbon capture because you get a really pure stream of CO2 that's amenable to...
Yeah, the big challenge with carbon capture is separating the carbon dioxide from all of the other gases. Something like a cement facility can have 10-20% CO2 in the stack. Most of the rest is nitrogen with a little bit of oxygen. But with a oxygen intensification, you get rid of the vast majority of that nitrogen, and you could have 50-80% CO2 in your stream, reducing the amount of volumes that you have, or the amount of volume you have to touch with the carbon capture, as well as the energy you need to input to capture that carbon. So yeah, absolutely. You're saving energy on the fuel input side of it, as well as making the potential for carbon capture far easier. And that applies to quite a few, especially of these high, anything pretty much furnace-based, where you have that direct heat transfer from a flame, and that's the main practical way of getting heat into it. Even if we were to use hydrogen for heating, because it's such a more expensive fuel than just using fossil fuels directly, we'd want to throw absolutely every intensification lever that we have at it. It's going to be worthwhile to minimize how much fuel that we need to use.
And so, I mean, my familiarity with these oxygen creating machines is in the medical field, home oxygen machines for palliative care patients, for instance, or people with severe lung disease. So this is just a markedly larger machine to do that. It sounds like, as you're saying, there's this huge efficiency to unlock. Why isn't it happening more yet, or is this something that is about to take off?
It is starting to show up, but it is a mature tech. You actually use different technology for that sort of medical application. I think you'd be typically using a pressure swing absorption for that, where for the really big scale stuff, you're using cryogenic. You're basically liquefying air, running it through distillation columns, and then regasifying that, using that cold to help liquefy the incoming air. But the minimum effective scale, you're starting to get into like hundreds of tons a day kind of stuff. So you're really talking big industrial users. Historically, the CapEx for those facilities has been fairly high, and fuels have been very cheap, and there hasn't been really much focus on minimizing the fuel side. I see much more interest in going to oxygen intensification, and a number of facilities that I've been involved with have either been designed with oxygen intensification from the ground up, or been, after a few years of operation, retrofitted with oxygen, either partially or fully, to increase the capacity as well as reduce the fuel usage.
Interesting.
So it is coming. Probably one of the more stealthy approaches. It doesn't hit many of the buzzwords in the electrotech stack. It's sort of the old technology approach, but with scale and repeatability, the costs come down. And as the focus is on more electrical availability and potentially scarcer or more expensive fuels, the balance really starts to shift.
With the process like that, I mean, I feel like we're heading into a lot of electricity scarcity as well with the AI boom, and increasing demand and old rickety power plants, some of which are being taken offline. For a process like creating oxygen this way, is this something that's amenable to cheap renewables that can run intermittently?
It's more, but you still have a minimum turn down before you start running into significant startup times. But you can vary the input within its operating range significantly more. You also, at a cost, can store liquid oxygen or liquid nitrogen product to regasify later to keep a downstream process working. So this is sort of that intermediate flexibility where if we get into a mix of firm, clean baseload and variable intermittent renewables, there are processes that can absorb a decent amount of that without excessive electrical side storage requirements, instead transforming that into much cheaper chemical storage. So that kind of process combined with a enough baseload capable supply, however you do that, whether through some combination of generation and storage, move through the value chain of that, and you can find a little bit more flexibility each stage you go to end out supplying the very stable energy needed for some of these pillars of the industrial economy.
Let's talk a little bit about electric direct heating, electric arc. Again, this requires my previous episode on this topic with Noah Retberg. He was saying, we're really just we've undersupplied ourselves with electricity to run a lot of these processes, and we've talked about that a little bit with the oxygen separation. But in terms of electric arc heating, pretty power intensive. We do use it a lot, I understand, for secondary steel production. Is there room for a lot of growth there to try and decarbonize some of these high temperature processes? And if so, which ones?
Steel is the most obvious example. We already talked about that, where you switch to processes that create direct iron, or there's potentially the some electrochemical processes, kind of like making aluminum, where you make an iron salt and you electrowin it out. That's much more lower readiness levels, but that's kind of the decarbonization path. For ammonia, we already talked about it, but it is essentially via some form of electrolysis, make hydrogen, and then the rest is pretty known tech downstream of that for ammonia. Cement's probably one of the more challenging because you fundamentally need that roughly 1400 degrees end temperature to partially melt the calcium oxide into the clinker. So you fundamentally need to be able to achieve that temperature, and even other ways of skipping the limestone part of it don't get around that very high temperature part. So we're probably looking at some combination of material substitution to get away from releasing CO2 from the limestone, or indirect heating of the limestone at the roughly 600 degrees that you need for that stage, and then, or oxy intensifying that stage so that you can have a much higher strength CO2 stream to capture, as well as then some form of likely fueled combustion for the kiln stage, the very high temperature part, where you can do that by hydrogen. Again, oxygen intensification would help there. You could do it by biomass derived fuels so that it's, the CO2 being released is going to be taken up somewhere and have a closed cycle instead of the open cycle. Or you can do some form of carbon capture on the kiln side of it as well. Ultimately, that's probably the most challenging and sort of the hardest to move away from that old tech aspect of it.
I guess maybe in closing, what is your take? We talked about how 25% of the world's emissions are industrial, 2/3 are process heat related. Looking forward, with a realist lens on, I know sometimes that's hard for engineers because you guys are brilliant problem solvers and can see a lot of potential ways through a problem. But I guess realistically also, with your experience looking at the economics of projects, what's your view looking forward, to 2050 or 2100 in terms of how much we could decarbonize process heat? Again, probably about 10 or 11 gigatons of CO2 per year in terms of what we currently put out.
in the very long, like 2100 timeframe, we probably can decarbonize the vast majority of it if we want to. The part of the challenge is the very long lifetime of the existing facilities and how long they take to depreciate. And retrofitting existing facilities is hard. They're designed for certain process conditions. Changing them tends to have fairly limited results. So we're kind of waiting for the turnover of the fleet, as it were. And some of these have 50, even 80-year lifespans. Really what we need to be doing as new facilities are built and the old ones age out, to be building them in mind with, if not immediately decarbonized, ones that are easily retrofittable to be decarbonized. So that would be like a natural gas DRI-based iron production with designing in the flexibility to use hydrogen down the line. Then that facility isn't your bottleneck. It's the upstream part of supplying the clean energy in the form of clean hydrogen. And to the extent that's possible, anything that can be electrified can be retrofitted later to use cleaner electricity just by having cleaner electricity on the grid. And, from that aspect, that's one of the reasons why I think a significant amount of nuclear is so important, is to provide that high volume of steadily available electricity that many of these processes need. And I mean, we talked about how they have a certain amount of flexibility that can be built through to accommodate some variability, but that's a lot easier when you're using that flexibility to accommodate demand variability for things like building heating based on the weather or air conditioning and stuff like that, than also accommodating too much on the supply variability side. It just gets steadily harder as we go. Then the other aspect is we use an enormous amount of steam. We will continue to use an enormous amount of steam, since nuclear inherently makes either steam or something that can be easily made into steam before you make electricity. The effective equivalent of a coefficient of performance you get on a heat pump for turning nuclear heat into usable process steam, you're effectively reducing how much power you can produce, but that ratio tends to be much higher than a heat pump can produce for an equivalent temperature output. So for a heat pump producing 150 degrees C, you might be in a very good case to be able to get twice the amount of heat in that steam as the electricity you put in, probably a bit less than that. Where if you're avoiding making electricity and instead exporting that 150 degrees C steam, you can easily get a effective 4 times amount of steam output versus the amount of electrical power foregone, and it does not depend on your ambient temperature. So you'd still be able to provide that 4 times factor when it's minus 40 degrees C outside. And that factor goes up as you go down towards district heating kinds of temperatures, where you can get up towards the 7 to 10 ratio. And that's one of the particularly large values would be for users of lower temperature heat, that we just need a lot of it a lot of the time. Nuclear, or to an extent some of the new geothermal, can output enormous volumes of that lower temperature heat without a lot of the complexity that going to the really high temperatures involves. From that standpoint, to the extent that we can electrify that, then nuclear and those other sources contribute by providing steady electricity to use.
I mean, in terms of these uses for very lower quality temperature steam, such as district heating, part of it is building the reactors, but a big part of that is the infrastructure in terms of actually distributing that steam. Luckily, it can travel a long distance, but it's certain Nordic countries are blessed, and I guess certain former sort of Soviet countries, they especially in northern climes, they did have a lot of these district heating systems set up, but that I think becomes a big challenge for places like where we live here in Canada and Toronto, for instance. I think downtown there's a few loops like that, but not as amenable.
My view on the decarbonization is the question, it comes down to peak heating. How do we deal with peak heating? Peak heat demand, not just process heat, but building and residential and commercial heat. However we deal with that really sets the shape of what a decarbonized energy system looks like. Because any system that can deal with that peak heat then has all of the elements it needs to deal with pretty much any other conditions.
I guess last question, prospects for nuclear within process heat more broadly. It sounds like from our discussion of high temperature gas to gas secondary loop to whatever process it is, we're limited in terms of co-location on sites. We just can't move it very far. We have huge heat exchangers. We have unaffordium alloys that are required. Lots of barriers there. So it doesn't seem like there's a huge near-term market for those sorts of applications. But we talked about high temperature steam. Seems like there's room there, and we have Dow Chemical and X-Energy working on that. Presumably a lot of things they can do at that refinery. We didn't talk, I think, about upgrading steam from conventional nuclear power plants, like 300-degree steam, whether that can be superheated somewhere else and used. I think when we look for where the future of sort of alternative energy is, we see those dreams we fantasize here in the West and sort of see them come true in places like China, where they're doing this for a variety of reasons, not necessarily decarbonization reasons, but more sort of fuel security reasons. So maybe we could just close discussing those topics.
Yeah, I mean, I guess directly upgrading steam is challenging. You can do it with essentially a compressor, but it takes a lot of equipment and electrical input to drive that. So generally you're only doing that if you have a very, a relatively limited upgrade needed and a very specific need for that particular temperature. Take a step further back and say, the vast majority of heat needs can already be covered by water-cooled reactor type output temperatures. 40 to 60 bar steam at up to 300 degrees gets you an enormous part of the way there. You're getting into the more specialty uses as you go to the higher temperature than that. The other interesting way to upgrade, though, is China is doing a project where they pair two Hulong 1s with one high temperature gas reactor. So the roughly 3 gigawatts worth of high pressure saturated steam is then superheated by 600 megawatts worth of much higher temperature process to provide that final bit of superheat temperature to then use in a petrochemical facility. So in that case, you're getting your lower fuel cost, conventional, large scale light water reactors to provide 80-85% of the energy and that much of the proportion of the fuel use, and saving your premium fuel for the last little bit where that extra bit of temperature really adds value. I'm very fascinated to see when that actually gets constructed and operating, but it's certainly the kind of clever thinking to minimize the costs instead of trying to do a one-step direct approach where you're using expensive fuel for your fairly basic lift up to 250 or 300 degrees C. Use the cheapest possible fuel for that part of it.
Right. And we will have an episode coming up soon with François Morin, the director, the China director for World Nuclear Association, exploring a little bit more the high temperature gas reactor program there. So hopefully we'll have some breaking news and cutting edge analysis for you, Jesse, and more broadly for the Decouple community. Thanks again for coming on today. I learned a lot. I mean, it's an area where for a non-engineer, there's a lot to get your head around. It's daunting to do this in one episode, but I think we did more than scratch the surface here today.
Every single part of it has its own wrinkles and complications. That's what makes it particularly challenging. It's not, a category that you can call a category. Every process has its own unique twists to it, and that's what makes it, challenging, but also what it makes it worthwhile. So thank you for having me on, and hopefully until next time.
All right, we'll score a hat trick one of these days soon, Jesse. Thanks again. Today's episode was made possible through a generous donation from the Xerxes Foundation and from listeners like you making pledges on our Substack. If you'd like to join the tribe, please do head over to our Substack, smash that pledge button, or if you would like a tax-deductible receipt, you can hit the donate button and make a contribution to our fiscal sponsor. We genuinely appreciate your support. It is only through your generosity that we are able to continue to offer energy literacy on demand.